our OmniSep battery separator today. And the name of the company is Magnera, which is probably new to everybody, but that was formed on November the 4th of last year between a predecessor company that I worked for, which is Glatfelter, and which was founded in 1864, and formed by a merger with a division of Berry Global. And Magnera is now the world's largest manufacturer of nonwovens. That's a material that's not readily known to the battery industry, but nonwovens are any kind of fabric that isn't made with threads and woven. We have about 25 production platforms based on nonwoven technology. We're 3.7 billion in sales with over 9,000 employees, 46 locations globally. Just a quick bio about me. I began my career in the battery business in 1981. Did a lot of projects with DoD, aerospace, electric vehicles. Back then, they were, of course, primarily based on lead acid, so they could get maybe 25 or 50 miles per charge, which is why they didn't commercialize. Primary lithium chemistries, and I've led this OmniSep project for the last 4 years. This is just a graphic of who Magnera is. This is our footprint. We have 46 facilities worldwide. We're headquartered in Charlotte, North Carolina. These are, it's interesting, post-merger, as I've learned about the technologies and processes that were part of the former Berry Global nonwovens business, I found a lot of applications for their technologies. You see them spun melt, air laid, wet laid, spun laced, melt blown, needle punch, etc. And I attended the Battery Council International show early this week in San Antonio, which is a lead acid battery trade group, and found actually a lot of applications in that industry for these new technologies. We have our advanced battery technology group and laboratory in Old Hickory, Tennessee. This is a former DuPont facility. And having spoken of a lot of the global nature of the company, we're fully IRA and infrastructure bill compliant, which was the reason why I was invited to this forum to talk about onshoring the supply chain in the US. So on the left, you see a stylized example, this top being a side view and this being a kind of top view of our OmniSep separator. It's comprised of a highly tortuous network of fibers that are basically consolidated and made into the separator. And in contrast, this is a stretched film, and it might be of interest to understand this a little bit, to understand the difference. So these things that are running in the cross direction that look like rungs, those are actually crystalline portions of the polypropylene that is made, that is used as the base to make stretch film separators, such as the cell guard. And these little teeny tendrils here, it's actually the amorphous part of the polymer. And when those are stretched in this direction, there's a separation between, or breakage between, the adjacent crystalline areas, and these little tendrils are what actually form the pores. So in a single layer separator, like a 2500, for example, these pores are all the way through. They're teeny, about 100 nanometers on square. They're a little more rectangular, but this is a contrast between the two, between our separator being fiber-based and a stretched film. So the process that we've developed is Omnicep is made of continuous fibers, these meaning they have basically no ending or beginning, of materials that we can process by high volume process. We choose the raw materials based on the temperature range that we want to achieve, chemical resistance that'd be important for aggressive electrolytes such as aluminum ion, for example, strength and functionalization. That would include things like either faster electrolyte wet out or aqueous systems. We can adjust all those. That is actually the reason for the name of Omnicep, because it's if you will, your everything separator. It can be adapted to the use case. It's important. We've spent a lot of effort to deposit these uniformly and consolidate them to the proper desired porosity and pore size. This structure gives an interconnected pore structure, high porosity and void volume that provides a low resistance to airflow or electrolyte flow, giving fast charge and discharge, low temperature performance because the thickened electrolyte can move through the separator more easily, fast electrolyte wet out, and that is important for things like fill rate, dimensional stability, and because there are no induced stresses caused by the stretching that I described earlier, and we have versions that are temperature stable over 200 degrees. So to look at some of the key properties, on the right-hand side, you can see this compares our Omnicep 12 micron, 15 micron, and 22 micron. And at 120 degrees C, these are published. This is published data for the stretch film separator. You see the degree of shrinkage back at, move that out of the way, 14%. The air permeability is very interesting. The industry reports using units of seconds per 100 milliliters. This is the Gurley number. CellGuard is 200. You can see how much more open our material is to airflow. We use a different testing method called the TechTex, which is common in the textile and nonwoven market. That gives us a better range of relevant numbers. You can see how the number is very low compared to our extremely high porosity and airflow. What's interesting, and the reason that I pointed out these rungs or areas of crystallinity in the stretched film, is that on a calculated basis, the porosity, which is basically the density or amount of void volume, is not that far off as it, in comparison to the actual airflow rates or electrolyte flow capability. So these pictures illustrate this point very well. This is the Omnicep 22 micron after 1 minute of a 0.25 mils of standard electrolyte. This is the 25 micron stretched film, and you can see that little droplet still remains. The This shows the, in this top row, our Omnicep 15 micron at 120 degrees C for 1 hour. You see the great difference between a 20 micron stretched film and at 150 C, because the fibers are both basically randomly oriented and not under stress, very little shrinkage compared to a stretched film separator shrinking 28% in the MD. This is what exposes the edges of the electrodes and causes direct shorts. Very important is the performance. We made our cells, of course, we had to plan our testing regimen several years ago. At that time, NMC 811 was the predominant chemistry, which is why we chose that. It's also less forgiving, as you know. So these top two lines, the 15 micron and 22 micron Omnicep, and these bottom two lines are 2500 and 1611. We chose those as the reference to compare the highest charge rate stretched film versus Omnicep, and we have the rate capacity retention shown here, 90 out to here 94%. For the battery experts on the call, we left the actual data here and only going down to 1400. If it went down all the way down to zero, this would these two lines would almost be on top of each other. But we wanted to give the actual data. So this shows that at C/3 rate, we're at least as good as the best. To get additional data, we changed the cycling rate to 1C to try to tease apart differences. And as you can see, there's the immediate drop in capacity at the 1C charge rate. But again, the Omnicep compared to be at least as good as the best stretched film for that use case. And finally, we took other cells and increased the temperature. This was the objective of this was to get as much data from the cell build as we could. Increased to 45 degrees C. You see this cell guard completely fell off here. This is the Omnicep and the cell guard. So in these three use cases, we were comparable. Trying to tease apart rate capability, we used first a C/3, C/2, C, 2C, 3C, going back to C/3, comparing the two, the Omnicep with the cell guard, they're virtually identical. Another test was the 30-second pulse discharge, going from C/2, C, 2C, 4C, 8, 12, and 16. And there was a decline, but they were virtually the same. Where we found actual differences was at the low temperature, because there we hypothesized that the increase in viscosity of the electrolyte at the low temperature, it was easier for electrolyte motility and ionic conductivity in the more open structure of the Omnicep in the stretched film. And there was approximately a 30% increase in energy output of the cell at -30. I mentioned the high temperature development. We have several different separators that we've made that withstand the 200 degree. This is the standard dry process stretched film separator, polypropylene based. This is the Omnicep high temperature. after 200 degrees for an hour, zero shrinkage in the MD or CD, and these two little dots right here are the molten little blobs of polypropylene of the stretched film. We've developed a shutdown capability. In EVs, there's interest in both having a high temperature resistance, but also being able to shut down before you ever reach that. So we've been able to make a derivative of the Omnicep, shows the electrical resistance before a shutdown temperature of about 125 C, and then afterwards the great increase in resistance, basically shutting down the cell to give additional safety. The capabilities of the Omnicep platform are the ability to adjust the pore size and porosity to match performance and end use or use case, all the way from very fast charge rates for things like drones and EVs to very long life self-discharge resistance. As I mentioned, we can functionalize the surface for electrolyte wet out, which reduces internal resistance, to provide fast filling for production and also use cases that need that. We're involved with a number of aqueous applications that I'll mention. We have dendrite suppression technologies that I can share in more detail individually. Some of these came out of learnings from the lead acid business that Gladfelter and I had been involved with for many years. We're able to apply coatings to Omnicep. Could be, for example, ceramic coatings to achieve very high temperature safety. Also for use in lithium metal anode applications where it's important to protect the separator from the reactive lithium node. We can also apply adhesive layers to facilitate cell production. We have technology to scavenge HF that's created due to carryover of water into the cell for any reason, to provide extended life. I mentioned the shutdown separator and the low temperature performance. So our commercial status, we've been making Omnicep regularly. It's a very highly reproducible process for the last 3 years on semi-production equipment. We have many engagements with our adaptability and the modifiability of the process and platform lends itself to military applications, high rate, UAV, DEWs, also where safety is involved with CWBs. I'm very active with MPSC and gave a presentation at CREB in January, Center for Research on Extreme Batteries. We also work with DevCom. Working with high energy materials, as I mentioned, lithium metal and silicon anodes, and emerging chemistries such as zinc manganese dioxide ion, aluminum ion, sodium ion flow batteries, and the lithium metal anodes that I referenced. We are the separator partner for Beacons, which is a which is at the University of Texas, Dallas. We had the ribbon cutting ceremony a couple weeks ago. That's supported by a $56 million investment by the Department of Defense, and ongoing supported by the DoD. Clients can go there to prototype on this very state-of-the-art facility that has coating capability, prismatic, and certainly coined cylindrical cells and pouch cells. So people will be able to go there, and we'll be working with them directly on projects. We have an extensive inventory of 12, 15, and 22 micron Omnicep available for sampling, and we can scale up to small scale commercial very quickly. So that is the end of my presentation. I want to thank everybody for spending their time to listen to this presentation. And at this point, I'd open it up for any questions.